basically, right, and pull out constants out of the L. If you can do that, then it's a linear transformation. But again, it's like a function that takes in vectors and spits out vectors. And then we saw that linear transformations can be matrices, right? The matrix is a linear transformation. However, not every linear transformation is not every linear transformation is a matrix, but every matrix is a linear transformation, right? And we saw an example of that, right? So with this one, actually, we saw that the derivative is a linear transformation from the vector space of continuous functions to continuous functions. And obviously that is not a matrix, right? So it's a linear transformation doesn't have to be a matrix. And then we talked about the integral as well, right? The integral is also a linear transformation.
He never doubted him.
Okay, now let's talk about something called the kernel in the image. So this is the analog of what is the null space and the column space for a matrix. Okay, so so definition. So let's say so let T from V to W be a linear transformation. So, and it goes from a vector space V to a vector space W, right? Then the kernel, which we say ker of T, is the set of all vectors X and V such that T of X is equal to 0 in W. Okay, so you can think of it as every vector that the linear transformation maps to 0. So this is called the kernel of T. Okay, so again, the picture goes like this. What's actually, so if you think of every vector, so here's V, here's W, and here's the 0 vector. So everything, all the vectors that map to this space right here is the kernel of T, right? So everything that maps to 0 is the kernel. Okay, so if, for example, the linear transformation was a matrix, right? If the linear transformation was a matrix, then that corresponds exactly to the null space of A, right? So, like say T was defined as T of X equals AX. Then the kernel is exactly this. So suppose that, let's say T from Rn to Rm is defined as T of X is equal to AX, where this is a n by m matrix right here, okay? Then the kernel of T is exactly the null space of A. Okay. All right, let's start off with an example then. So now the question becomes, how do we find kernels in general? And the answer is there's no direct way. However, you just literally see what gets mapped to 0. Okay, so let's start off with a simple example. So let's say we had the vector T that goes from, I don't know, let's say the set of 3 by 2 matrices with real entries, the vector, yeah, and this one goes to a set of 2 by 3 matrices with real entries. Defined as T of A is equal to T A transpose, okay? So remember, we showed that this was a linear transformation last time. Now, find curve of T. Okay, so let me ask you, what is acting like a zero vector in the space of matrices? With the standard addition, you know, you add matrices component-wise. So I guess a better question would be, so let's see, let me put this, over here, and I should probably say like example 6.21 anyway, so so solution, we need to find every matrix A transpose. Like, you take the matrix A and interchange the columns and rows, and then once you do that, that would be the transpose. Every matrix A such that T of A is equal to 0. So what are the matrices that get sent to 0 by T? Well, we have that T of A is equal to A transpose, right? And this has to be 0. So what is the only way that you get A transpose to be 0? If A is 0, right? This is if and only if A is equal to the 0 matrix. So what is, okay, so then the kernel, so the kernel of T would equal what? What would the kernel of T contain? The what? Yeah, exactly. The 0 matrix, right? The 0 matrix. So, I mean, this is what you look for. In general, when you're trying to find the kernel of a transformation, you try to look for everything that gets mapped to 0. There's no straightforward algorithmic way to find it if it's not, I mean, for the transformation AX, yes, you just find the null space, right? You RREF and you find the null space, and that'll give you the kernel. But if it's not something that if it's like, you know, something like this, right, which is a transformation that isn't like a AX, well, how do you do it? Well, like this. You just try to see what everything gets mapped to 0. Okay. So let's see. All right, so let's look at another example. 6.1.2. And let's say we had two things. Find the kernel for the following. So A, T from V to V is the identity. And then B, T from R3 to R3 is T of, I guess we can say, T of the vector x, y, z. And this gives me the vector x, y, 0. All right. So for A, what does it mean to be the identity? Well, I guess in a general sense, for the identity matrix, why did we call it the identity? Because any matrix times that gave me the matrix itself, right? Like A times I equals A. What is the identity for real numbers under addition? Well, 0, right? Any number plus 0 is the number itself, right? So the identity here just means take x, put it inside t, and it gives me back x, all right? So the identity is expressed as t of x is equal to x, okay? So it just, you give it the vector, and it gives me back the vector. That's where it is, okay? So what is the kernel of this thing? Yeah. The only thing that could get mapped to it is if I give it the 0 vector, it'll give me back the 0 vector. Is any other vector that's not 0 that would give me the 0 vector? Of course not, right? It's just going to give me back the vector itself. So if I guess you say the only one vector that works that will give 0 is if x is equal to 0 in the vector space, right? So the kernel of T in this case is also just a 0 vector. Okay. Okay, what about the next one? So this linear transformation has the rule, you give it a vector, it gives it back to me with the first 2 components, but the third one makes it 0, okay? So let's see. So B for, I guess, T of x, y, z is equal to x, y, 0. What is the only thing, I guess, what is the only thing that would give, well, not that, that's actually a million things that would give it to me. What are the things that would give me the 0 vector? So we need to find all vectors x, y, z in R3 such that T of x, y, z is equal to 0. In other words, just the 0, 0, 0, right? So that, yeah, exactly, yeah. If I pick, for sure I need to pick x and y to be 0, right? But z doesn't matter, right? Because if z is like 5, the transformation just tells me I'm going to make it 0 anyway. So any vector of the form 0, 0, z, where z is a real number, will do. So the kernel in this case is equal to the set of all vectors 0, 0, z, such that z is a real number. Perfect. All right. Let's do one more, and then we'll basically start doing more things. Let's see. So let's see, example 6.1.3. Find the kernel of T that maps from R2 to R3 in the following way. So it takes a vector x, y, and it spits out the vector x minus 2y, 0, and minus x. Okay? So solution. So we need T of x, y to be equal to 0, 0, 0, right? Or in other words, I need x minus 2y, 0 minus x is equal to 0, 0, 0, right? Well, from here, we get the system of equations. X minus 2y is equal to 0. 0 equals 0, doesn't matter. And then minus x is equal to 0. So from there, you can see that x has to be 0. And, sorry, hold on a minute. Well, yeah, x has to be 0, which means that since x is equal to 2y, y also has to be 0, right? So x has to be 0, and y also has to be 0. So the kernel, which I'll do right now, so the kernel of T is just going to be the vector 0, 0. That's the only one that gets mapped to 0. All right. All right, so now we know more concretely with what is the kernel of a transformation. So now we're going to state a theorem that is going to be useful, right? So it turns out that the kernel is actually a subspace, right? So theorem 6.1.1. The kernel of yeah, sure. Well, but basically what I'm going to write down is the kernel of a linear transformation T from V to W, a linear transformation. T from V to W is a subspace of V. Okay, so if it's a subspace, what must it have then? Spend a long time talking about this for subspaces or even vector spaces in general. So I mean it has an addition and all that, but what's one important thing that we always want to have, we always like to have, well, it has it because it's a vector space, but it has a basis, right? Remember, anything that's a subspace or a vector space will have a basis. Since this is a subspace, that already tells you it's going to have a basis. So the next thing we're going to do is basically want to find basis for kernels. So this tells us that that curve of T has a basis. Okay, so and basically the running example is like for example, if T of x is equal to ax, then to get a basis for per of t is the same thing as getting a basis for the null space of A. Remember how you find the basis for a null space? You just RREF it, solve it, and then however you get, you express it in vector form, the solution. The two or the vectors that are like there as a span, those are the bases. So basically the same thing. So let's see. There's no need to say that. Let's do one more theorem. It also turns out that the well, hold on. Sorry, let me define something first. So definition: the image of a linear transformation T from V to W is per of T. Oh, sorry, not is denoted as the IM of T, which is a set of all W in W, such that there exists a V. Oops, there exists. Well, actually, not even. But just T of V is equal to W. That's literally all it is. So it means that in the image or in the range, you pick a vector. If there's something that gets mapped to it by V, then it's in the image. So just like the range of a function, right? So let me make this. So it also turns out 6.1.2 that the image of a linear transformation, yeah, there you go. But so basically what I was going to write down is basically that the image of a linear transformation T from V to W is also a subspace, which means it also has a basis. And if you translate that to the linear transformation defined by AX, that's just finding the basis for the column space. So you guys know how to do that now, right? So you RREF it, every column that has a pivot point, look at where it's at in the original matrix and take those two vectors and that's your basis. So the image of a linear transformation is from T to V to W is a subspace of W. So notice that this one is a subspace for W and the other one is a subspace for V. So one lives in the domain, one lives in the codomain. So don't get those two confused. So I guess let me just mention it. If T is from Rn to Rm is defined as T of X equals AX, where A is an m by n matrix, then the image of T is equal to the column space of A, and to get a basis for T is the same as getting a basis for the column space of A, which you know how to do now, right? So let's see. Okay, so there's 2 more things or 3 more things I want to talk about in this section. But basically everything we're doing right now is basically we're generalizing a little bit more with column space and rows and the null spaces. All right, so do you guys remember what dimension basically for a vector space? Just it's the number of basis elements that make it up, right? So do you remember what how we defined nullity and the rank of a matrix? The nullity was the dimension of the null space, and the rank was the dimension of the column space, right? Well, we have the exact same thing for linear transformations, and it's defined the exact same way. So, definition. So let T from V to W be a linear transformation. So we'll say the nullity of T, which we call, I guess, null of T, is the dimension of the kernel of T. Okay. 2, the rank of T, which is what we'll call rank of T, is the dimension of the image of T. Okay. So same thing. So remember if T was the typical AX, it just says the nullity is the rank, is the dimension of the null space, and the rank is the dimension of the column space. If you were to take the specific case of T of X equals AX, right? And in a similar way, we have a rank nullity theorem for it. So remember, it just tells you that the dimension of the null space, well, for the matrices, the dimension of the null space plus the dimension of the column space has to add up to the total dimension of let's see. So I guess if you had a n by n matrix, it would have to equal the let me see. Sorry, hold on. Let me see. Yeah, that's right. It would have to equal the dimension of the vector space in the domain. So here, let me just write it down. So So this would be 6.1.3. Okay, I guess you can say let T from V to W be a linear transformation. Where I guess we can say V and W are n-dimensional. Then then I guess you can say the dimension of the image and the kernel add up to the dimension of the vector space and to the domain of the vector space that's the domain. So you can say the rank of T plus the nullity of T will equal n. All right, so that's basically what it says. So so this stuff, I'm not doing examples because you literally have done it before. It's just the case where it's more general, right? It's a linear transformation. Basically, where it gets useful is you'll see later on when we start talking about matrix representations of linear transformation. Because once we have that, then all of this becomes almost trivial. All this right now is super abstract. Like, who cares, right? But once we get to the matrix representation of linear transformations, it'll all make sense, hopefully. Yes. All right. So, do you guys remember for like in college algebra when they talked about functions, they just told you, oh, this function's one-to-one? Do you remember what that means? Like something is one-to-one or onto or injective or surjective? Yeah. So for every input, for every output, there's exactly one input, right? Like f of x equals x squared, right? The output 4 has two inputs, 2 and -2, right? So that's not one-to-one. So anything that has, for every output, there's exactly one input is what it means to be one-to-one for just normal functions, right? Well, we have a similar notion here, and it's exactly the same thing. For every output, there's exactly one input, kind of thing. But, oops, I waited too long. Sorry about that. Oh, wrong one. Sure. But the difference from there to here is that if we have one-to-one, since we have structure on our space, that immediately implies so many things about our linear transformation. So next is a important result. So this one is especially important. Okay. So definition: a linear transformation T from V to W is called injective or one-to-one. That's what they say. If for every W and W, there exists a unique V and V such that T of V is equal to W. That's what it means. Okay, there's exactly one. For every output, there's exactly one input. So I guess the running example that you always seen in places is basically, you have like, say those are my three vectors. T maps to exactly 1, like this, 1 and 1. This is 1 to 1, right? Injective. If it was like, if one of them went to two of them, it wouldn't be. Now here is the important part. So this theorem is what would basically give us a lot of things. So it turns out that if the kernel, so you remember how we were computing kernels in the like 3 examples? Remember how like one of them had exactly only one thing in it, which was a 0 vector? So if that happens, you don't even have to check this definition. If that happens, your linear transformation is immediately 1 to 1. Okay. So theorem 6. Oh, sorry, 6.4. So for a linear transformation, T from V to W, if the kernel, better yet, the kernel of T only has the 0 vector if and only if T is injective. Okay? So, and even more powerful is if it's injective and you have V and W be finite dimensional vector spaces, it immediately implies that it's surjective as well. So what is it? So for functions, remember, how do you, for functions especially, when could you find the inverse of a function? I mean, could you always do it? So for example, like if I gave you f of x equals 2x plus 1, how would you find the inverse of that? So you had y equals 2x plus 1. Well, all you had to do was interchange the x and y and then solve for x again, right? And that new formula that you get is the inverse. But you couldn't always do this. You can only do this under the situation that f was 1 to 1, right? If it was bijective, which means it's also surjective. It's even better. But the reason I'm pointing this out is that if, for example, if t of x equals ax, right? A of x equals 0 only has the trivial solution, meaning, so this is, I guess this is where we're trying to connect it. So recall that if and only if, it goes right here. So t is injective. Oh, you can't see it? Sorry. So basically what I was going to write is basically, so recall that if for the matrix equation AX equals B, the equation has a unique solution if and only if AX equals 0 has only the trivial solution, right? What does that mean? It means x is equal to 0 is the only solution, right? But what does that mean, like in context of what we're doing? Well, that basically means that the kernel of T is equal to 0, where T of x is equal to AX, right? But if this has a unique solution, this also, but remember all the little results that we had. If this has a unique solution, it also means that this, so recall also that a inverse exists, right? If the AX equals 0 has only the trivial solution, right? But that's exactly the inverse of T, right? So knowing that the kernel of the transformation is 0, only contains a 0 vector, immediately implies that your transformation is invertible. It is, and I mean, it all makes sense in context of the transformation AX, right? We're basically getting all these notions out of all these linear transformations, right? So where's the other thing that I wanted to say? Oh, there it is. So let's look at some examples then, before we, I guess, completely. What example is this? 6.1.4. So let's do one. Is the transformation from, I guess, m by n matrices with real entries defined as T of A is equal to A transpose onto, oh sorry, injective? Okay, so what do you guys think? Is it injective? Yeah, why is it injective? Uh-huh. If it's equal to 0, and then so he says something about the kernel? Yeah, exactly. So the only thing that has that's in the kernel of this thing is 0, which by that theorem over there tells me it's 1-to-1. So you don't even have to like go and check if every output has a one input kind of thing, right? So solution, since the kernel of T is just equal to the 0, then T is injective. So we already did this example, like finding the kernel, like a couple, like maybe like 20 minutes ago, right? So okay, so we have 4 minutes left. So let's see. Today's the 19th. I think this is good pace because we're about to finish the section. So I think what I'll do is I'll end today right now. Basically, what we're going to do next is basically we're going to establish what isomorphisms are. All right. So as you might have noticed, the linear transformations can get kind of weird, right, if they're not matrices. So what we're going with this is that we're gonna define the notion of what bijection is, right? So remember in function land, functions bijective if it's injective and surjective, meaning it's 1-to-1 and onto, right? So that means that what that means is that so have you guys ever heard of like different size infinities? So if you can actually prove that the set of even numbers is exactly the same size as all the counting numbers. well, actually all the integers, like -1, 0, 1, 2, all of them. All the even numbers have the same number of elements as that set as well. And you can prove that using, okay. Perfect. Then you know, but yeah, but basically, at the end, basically the linear transformations, how they are right now, are not useful. We always like matrices, right? What we're doing right now is we're going to make it formal that every linear transformation from a finite dimensional vector space to a finite dimensional vector space, you can represent always as a matrix. And then once you're there, it's basically how you've always been working with matrices. You just do RREF and all that other stuff. So that's where we're going with this, basically. All right, you guys can go now. Actually, this one will actually take a little bit less since I only gave 4 questions without any parts. This will actually go by a little bit faster. So I suspect soon. I want to say what exact date, but this one shouldn't take as long as last one. Last one had like 15 questions I had like grade, and this one only really has 4. The final will be sometime after the 4th. I have to see when it is. I think I put in the syllabus actually. Not sure what day, but it's in there. Okay, the 7th. Okay, then it's the 7th. So it's in the syllabus. So it's, if this says the 7th in the syllabus, that's when we're gonna have the final. What time? I think it's also in the syllabus. So, all right. Any other questions? Yeah, 1:30. Perfect. Okay, so it's 1:30. 1:30 on the 7th. No, linear algebra is special in that every instructor does their own thing. Kind of, you mean you follow the university's guidelines, but you can always add in stuff that isn't there. So yeah, so it's. Do you know what time? I'm just gonna do all day. Actually, instead of just doing 1:30, I'm just gonna do all day again. It's just gonna be a take-home final. So you guys have all day to do it. So no, yeah, but yeah, to answer the person, no, not every linear algebra class takes the same final. Everybody does their own thing. So, any other questions, comments, concerns? Okay. Well, I guess if there's no more questions, then I will see you guys Wednesday. Oh. All right. See you guys later.